Don't need the first slide because before I start, some news that came overnight, I thought I was going to share them with you because I think it's interesting, some illustration of some of the things that we have discussed this morning. So overnight, we have seen an announcement that should be interesting for industry, for the also investors and policymakers. That there's a big unicorn in the United States that has been acquired by Marvell. It's very important in the photonics. I think all my photonics expert colleagues here have noticed the news. Why it is interesting, I think, for the discussion today, first is to realize that the inception of of what they are building is actually all coming from Europe. It's based on a technology that IMEC has developed already more than 10 years ago. And the starting point was a collaboration between the founder of Celestial and Nikos Pleiros in Greece. However, the whole success now is moving to the United States. It's not being done in Europe. But there's been seed funding also coming from Europe. So the question that I think we should ask ourselves is, how do we make this next Celestial AI being a European company and actually making beyond what they've done as they are disrupting the network in data centers and computing, and maybe becoming the next NVIDIA. So that should be our ambition, I think, as a community also here in Europe, to reflect on this and how do we do things differently in the future. Now, enough about Celestial AI. I will move to my presentation. Yeah, one thing that we have not discussed so much this morning, I think, is the power challenge that we are facing, as we are assuming that AI is going to drive all the chips, or 50% of the chip growth that we'll see in the next 5 years. It's only possible, I mean, if you can actually power up those chips. And so the power consumption increase associated with deployment of AI is also a very big challenge. I think we started to talk about it in the previous discussion. So as we see exponential growth in compute needs, we are seeing also an exponential growth in the energy consumption. And if we don't disrupt the technology, if we don't come up with fundamental different materials at the core of the technology, we are on a track of building chips that will sit on the shelf because there's no power to light them up. This is probably needed everywhere. So this is in AI data center, of course, and I will talk more about that, but also in edge AI and sensing. How do we improve on the sensing in order to reduce the AI that we need beyond the sensing to make sense of what we observe, and also in our industry manufacturing. So not only it's needed everywhere, but also at every level. So if you look at this diagram, that's kind of a generic representation of new systems that are being deployed, where you have compute closely packaged with memory and optical interface and sensors. You need this innovation at the various levels, and each of them have a roadmap. And I apologize, Ajit, I didn't bring the CMOS 2.0 roadmap of IMEC because I will more introduce the photonics part of the activities that we do. But indeed, IMEC is working closely with the industry to improve or to develop the technology that will go into the advanced nodes down to a few angstroms. What I will talk more about is on the technology we need to develop for the advanced IOs that we also need to improve in order to reduce power consumption in data centers. Also needed in custom sensors. I will not talk too much about it. I will touch a point on that. And of course, advanced packaging, that will be covered by other colleagues here. Now, in AI factories, I don't have a fancy diagram of AI factories, but in a nutshell, you have various lengths of your interconnect in data centers, and it goes from 2 kilometers to a few centimeters. And it's clear that for the long distance, optical prevail. There's almost no loss on an optical fiber, and that allows us, once the data is being transferred from electrical to optical domain, to be very efficient. And that's why optical prevail in the long distance. In the shorter distance, in orange here, electrical remain more efficient actually to to enable this interconnect. But there are some limits to it, and those are the limits that you see plotted on the graph. One disruption we have seen recently, actually this year, is when NVIDIA, and actually Jensen Huang himself has announced how important integrated photonics was for deploying his AI factory systems. And by disrupting some of the packaging constraints that existed before, they managed to actually improve by 10x the efficiency of the optical interconnects and their switches that they are deploying. Now, this is done at relatively long distance in the compute system. It's covering in the 100 meters. But there are roadmaps to improve and leverage packaging and advanced materials in order to improve by maybe 1 or 2 other magnitudes the efficiency of interconnect in data centers, not only for the long distance, but all the way within the compute nodes. An example for scalable optics is in pluggable optics, we are trying to cram as much as possible data rate onto a single fiber, and that is driving a certain roadmap in terms of introduction of new materials that are capable of surpass silicon that is currently the technology of reference in I would say, intermediate distance data centers. But material is not the only thing, also packaging solutions for having an optical connection to be as easy as an electrical connection. There's a lot of innovation that is needed also there.
This is asking for you to oversimplify something that everybody in this room except me probably understands.
Go ahead.
And that is, you mentioned optical gives us the capability of packaging lots of data over a given time. I have heard people who interpret that to mean that optical communications allows us to transmit stuff faster than the speed of light. Can you explain what makes data packaging much larger in optical communications than it does via regular electrical communications?
Yes, I can. So well, I think I can. I will try. Optical fiber, basically the light has more dimensions than electrons. And so you're using more dimensions actually to transmit the data. And the basic dimension that we're using in light is, for instance, wavelength. So by putting multiple wavelengths of channels on the same fiber, on the same physical medium, you can increase dramatically the bandwidth. So that's one way to really increase. Now, it's not faster than the speed of light,
no, yeah,
but you put a lot more on a single medium than you can with electrons. Yeah, and I talk about wavelength. Phase is another one. Polarization is another one. So it's a very rich physics environment to actually do data communication. Now pushing further into understanding how optical can displace electrical connection in systems, you can disrupt the current limitation of copper. And I know there's a lot of innovation in copper, but at some point it reaches its limits, and it cannot support multi-wavelength, as far as I know, for instance. So we are looking at IMEC at developing all the fundamental technologies in order to develop optical interposer systems. And we are not the only one doing that, of course. It's becoming more and more common as part of the roadmap in the industry, is to consider that on the board you will interface chips together with light as an interconnect. Now, of course, a lot of innovation is needed to make that happening, and that's why we have a very rich roadmap. And it's not a dimensional roadmap as we have in CMOS. It is mostly material roadmap, but also packaging roadmap, in order to reduce the photons that we lose, and in order to improve, and that's very important, the efficiency on when we implement the transducers from the electrical domain to the optical domain and vice versa. Today, these transducers are relatively inefficient, and there's a lot of work that we need to do, but we think there's a path forward. Now, there was a question on how IMEC is working with the industry in order to make changes. So there's a basic platform that IMEC has developed, and actually this has been developed, I think, with my team around 11 already 11 years ago, and we keep transferring that to advanced fabs. I think it's now present in 7 foundries, and directly or indirectly. So that's one thing that we did 10 years ago, and it is being put in production today. I'm again talking about 10 years it takes. But the difference is IMEC here, we have the ambition from day one, not only to do research on it, but to deliver prototypes and early production with this technology until the big foundries finally make up their mind and offer this as a technology. And this is what you see with Celestial AI, for instance. Now, we don't stop at this platform, of course. We also invest into more fundamental research, and we are exploring, okay, how do we disrupt this energy inefficient way of moving from electronic to photonics? This is one example of a Nature paper where we have demonstrated actually a laser on silicon in a very compact form factor. Now, it doesn't stop at AI factories. Photonics, we think, can have a large impact in other domains. In health, I will only apply one example here in the domain of genome sequencing, where actually adding optical waveguides on top of CMOS imagers can really accelerate long-read DNA sequencing. And this is again, a photonics on chip that is enabling that. On automotive also, I know Elon Musk is not a big believer in LiDAR, but we think that actually I should extend automotive to automotive and robotics. Precise remote sensing will be necessary, and we think that LiDAR type of approach will be beneficial. And if you look at LiDAR today, those are big systems. There's a need to make it very small, power efficient, and we think integrated photonics has a way to resolve that. Alternative compute, we haven't talked so much about quantum computing yet, but that's also a place where photonics can play a role. Of course, there are companies like PsiQuantum, Xanadu, looking at using the optical domain in order to do the compute itself, but optical will also play a role in the interconnect of systems that are using other medium for the compute. So that's another place where photonics, and this type of application is really pushing the limit of what the technology needs to deliver, as each photon has to be preserved, and all characteristics of the photon needs to be preserved within the system. Now we do that, and I will talk more about it tomorrow in a collaborative manner. So IMEC is collaborating with many of the colleagues here in the photonics domain. And you can see here an overview of all the projects that we have in Europe. And then I will extend one last word about IMEC in general. For those who don't know IMEC, IMEC has been driving a microchip roadmap for 40 years. IMEC is an independent research institute that is now considering being world leader in this type of work, where we try to be independent from the industry in terms of economical interest, but in terms of course, of research interest, we collaborate with all the industry. This is an image of IMEC campus in Leuven, in Belgium. And I think earlier this year was made official that we are expanding these facilities now with, there's a movie. I will skip the movie because it's too long, but the main point is actually it ends up in Malaga. The end of the movie is in Malaga, and that is because we are going to expand for the first time our clean room operation to outside Belgium. We'll install what we call Fab 5 in Spain, in Malaga. And with a very special focus is actually to accelerate innovation on new materials and doing it immediately on production equipment. So that's a key thing that we want to do, and we'll make it complementary to what we do in Leuven. And so now it's becoming more and more real. I was discussing with Antonio on some of the design work that is ongoing in Barcelona. Here in Malaga also, we are getting close to getting started with the real work and the real building. So that's my short introduction. I'm sorry, I was a little bit long, but I think it was also important to anchor.
No, it was great. It was wonderful. We all needed to get an introduction to photonics as opposed to photons as opposed to electrons. And join the stage, and thank you very much for
Thank you.
giving us that introduction. And then